Good morning, ladies and gentlemen. Sorry for my late welcome to the University of Cassino. I am always very glad to host in our university international conferences because it's really not so easy to convince colleagues coming from abroad to reach Cassino. We are not in Rome, we are not in Naples, and I know very well that it's not so easy to arrive here. But I'm also sure that you will enjoy the conference and the location. I thank Professor Porzio and his team for the effort in organizing the conference. I've heard that participants come from 21 nations, and it's really a great success for the reason I've said. Let me say some words about the conference topic. I'm an engineer. I teach and research on electrical and electronic measurement. So all my activity since I was youth was on data acquisition, on data processing, on data analysis. And for the reason I am very glad that recently words like big data, data fusion, data analysis, data science have become of common interest and use, sometimes even without real knowledge on them. I'm sure that your conference will give important contributes on these topics of great importance for our life. I am only one great regret. I will not be able to attend the conference, and thank you very much again for being here.
Thank you, Giovanni. Now is the time for Enrica Iannucci, the chair of our Department of Economics and Law that supported the conference and to which I belong.
Good morning. Good morning, Giovanni and Giovanni. Dear guests, ladies and gentlemen, I'd like to welcome each and everyone for being here today to the cladag International Conference held here at Cassino University, and it's the first time here. It's a very important international event for our university, but especially for our Department of Economy and Law. And so, before we get started, I'd like to express my thanksgiving, especially to Professor Porzio, to the scientific committee, Francesca, and all the other persons for managing this. I hope you will enjoy, and thanks again for being here. Thanks.
Thank you, Enrica. Yes, now the president of the cladag group, Roberto Rocci, University of Sapienza, since few days.
Thank you. Thank you, Giovanni. It is a pleasure for me to be here at the opening of the cladag meeting, edition number 12. I recall you that cladag means classification and data analysis group. So it means that it was born and it exists in order to promote the research on the fields of classification and data analysis that are pillars in statistics, but nowadays they are also fundamental pillars in data mining, machine learning, data science, deep learning, and so on. We are well recognized in doing that. At the Italian level, we are a section of the Italian Statistical Society. At the European level, we are a member of the European Conference on Data Analysis Network. At the global level, we are a member of the International Federation of Classification Societies. And we are well recognized because I think our activities, scientific activities, and mainly for our meetings that, as I said, now reached the number of 12. The first one was held in Pescara, mainly thanks to Maurizio Ichi, and it was a success. The second one was in Rome. I remember well this edition because I was a very young associate professor, deeply involved in the organization of that meeting, and we repeated the success of Pescara. Then from there started a long journey, a route with several stages. I have to read in order because I'm afraid to forget something. Palermo, Bologna, Parma, Macerata, Catania, Pavia, Modena and Reggio Emilia, Cagliari, and the last, Milano, and then now Cassino. During this very long route, the meeting has grown in terms of scientific contributions and the participation of researchers from abroad. And I'm sure that Cassino will confirm this positive trend. So in the end, let me thank all people that worked and are working on this stage, on this meeting, starting from Giovanni Porzio, the statistical team of the University of Cassino, and more in general, the University of Cassino, that here is represented by the rector and the chair of the department. Thank you very much for this wonderful organization. Francesca Greselin and the scientific program committee for the scientific program. But above all, let me thank you all the participants, because I'm sure that with your contribution, scientific contributions, you will make this meeting a success. So thank you very much. Thanks.
Francesca, last but not least, it's your turn. Please.
Estimated Chancellor of the Cassino University, Professor Giovanni Betta, we would say Magnifico Rettore in Italian, dear Professor Enrica Iannucci, Head of the Economics and Law Department of University of Cassino, dear Professor Roberto Rocci, our President, and all of you, distinguished scholars that came at cladag 2019, considering it as a venue for your research. I'm honored to be at that table for the opening of cladag 2019. The century that is ours is shaping up to be the century of data revolution, has been written by Boveron and colleagues in a recent book on model-based clustering. Our numerical world creates masses of data every day, and the volume of generated data is estimated to be doubling every 2 years. This wealth of available data offers hope for exploitation that may lead to great advances in areas such as health, science, transportation, defense, and in many others. Once more, progress in knowledge and sciences could improve life quality and give a contribution to our societies in such a delicate time. However, manipulating, analyzing, and extracting information from this data is made difficult, not only by its volume, but also by its nature. Modern information comes from high-dimensional data, oftentimes network data or time series, and other complex structures. These open a greater challenge for people like us who wants to mine, to understand, and interpret this data deluge. The present conference is a contribution to this challenge. We are blessed to have witnessed the great interest that the colloque paper has generated, and we thank all the authors for their contributions. We are, of course, grateful to other referees for their intense work during the selection process. We are indebted to the entire program committee for involving their scientific relationships, inviting distinguished scholars from 22 countries all around the world. This permitted to build up a very rich program for the conference. During these days, we will discuss themes which are at the frontier of research, like open issues in modern, multivariate, robust data analysis, in preference rankings, in functional data analysis, in multi-block data analysis, in the analysis of complex networks, of compositional data, of data streams, in method for directional data and for archetypal analysis. We will see how data and models are intrinsically related, and we will compare modern likelihood methods, parametric, semi-parametric, non-parametrics, and Bayesian methods. We will discuss their application in health, economics, finance, medicine, social studies, and so on. The scientific committee also nominated the 5 keynote speakers: Christophe Biernacki from University of Lille in Ria of France, Adrian Bowman from University of Glasgow, Scotland, Bettina Grun from Johannes Kepler Universitat Linz of Austria, Francesco Mola from University of Cagliari of Italy, and Sylvia Richardson from University of Cambridge, UK. I want to address each of them our warm gratefulness for the time and effort they took to come and share their remarkable thoughts and findings with this audience. A post-proceeding book of selected paper will be published after the conference within the Springer Book series, and a call for a special issue of the journal Statistical Analysis and Data Mining will also be opened at the conference. Finally, we are greatly indebted to the organizing committee, Giovanni Porzio and his team, Simona Balzano, Alfonso Iodice, Luisa Natale, Giuseppe Pandolfo, Renato Salvatore, and Domenico Vistocco. They made our work on the conference as easy as 1, 2, 3. But we would nevertheless be remiss if we did not especially mention the cladag president, Roberto Rocci, for his constant and frank advice that has guided our work. This year's event promises to be bigger, braver, and bolder than ever before. Now the conference is in our hands and minds. Let us shape it with our best participation. We will make it from now on.
Thank you so much to everybody. Just a few words, technical words. You should have a bag. Inside the bag there are 3 sheets of papers, one for each day with a summary of the program, and then the booklet with all the programs with all the names and titles. A small presentation of the orchestra that will play tonight, and that's it. I hope you will enjoy. Don't miss the social event tomorrow. Visit to the Abbey and nice dinner in a nice place, a middle-aged castle, just a couple, 20 minutes from here. Okay, so it's time to start with the scientific work. Thank you again. I will leave this room for the session that, according to the scheduling I have here, is recent methodological advances in finite mixture modeling with applications. The other sessions are in the other room, 1, 2, and 3. You will find the arrow. I hope you don't get lost. For any trouble, please ask me or anyone else from the organized committee. So let's enjoy the conference.
strategia, ma poi l'ha pensata da lontano. Senti, tanto ci vediamo dopo. Grazie, ciao.
I'm quite sure.
Are you plugging in? Okay, hold on. Maybe I can. Do you want yours on this? Oh, you're in a different one.
Però pendolo giù.
Tutto a posto? Io sono stato cazzo cosa dice tornare a Roma e adesso dal 3 settembre
Crescere
Io ricordo. Sì, stai pensando a Ah, ecco.
So you're going to use this computer or that?
This one. There's no.
Yeah.
Something different.
Renato.
Oh, okay. Fantastic. We're trying. Like we have one and
Okay. Yes. Do you have the presentation on the pen drive or?
get it. Are you copying? Yeah, he'll give it pen drive.
I think this is it. Okay.
Ok.
Okay.
So this is you. This is mine.
Okay. And then there is a third one, I guess. Okay. Just. Thank you. Okay.
You have to start the session. Ah,
Okay. This is it. Okay.
So this 1, 2, 3. Right?
Yes. So you will start first and then.
This is the first one.
This?
Then this one.
Okay. So let's put it like that to do not. Okay.
How much time should we try to shrink a little?
Try to shrink if possible, because then we have the plenary. Depends on your.
Yeah, we'll.
Maybe you, because this is
Yeah, I will try
it's a
to make
pity
it
to
1 hour.
make. But we have a coffee break, so maybe we can install something, steal something from the. What do you think?
I will try to finish.
Yeah. It's, yeah.
Also short, not the
We prefer to listen to the contribution instead.
Okay. So this is yours, I think.
Tanti lavori infatti lo stesso.
there is other rates.
No, ma i motori sono quelli, vabbè, si deve liberare questa parte, cioè è una di quelle intersezioni dove anzi sarebbe inutile informazioni diverse.
Sì, però ormai è diventato il fatto della data science, è diventato anche un po' un dovere.
Ieri ero a Roma, la funzione di arte era ancora non si fa Windows, ma si sa quando abbiamo scoperto di essere rapporti collegati. Eravamo stasera, quest'estate eravamo a casa la stessa cosa.
One of the very first sessions, right? One of the first sessions in cladag. We have three speakers. We have a speaker, Michael Gallagher from McMaster University. We have a speaker, Eric Page from Brigham University, and also there is speaker Martin Porter from the University of Virginia. And the first talk will be given by Michael on skew distributions and transformations, handling skewed data and cluster analysis. We will try to shrink our session a little bit just to get a little bit better schedule. So please, Mike.
Okay. So thank you, Dr. Melnikov, for the invitation. So today I'm going to be talking about some collaborative work I did at the University of Alabama with Dr. Melnikov. And basically a detailed comparison between using either skewed distributions in a mixture model or performing a transformation to near normality and clustering simultaneously. So I'll begin with an introduction, then I'll look at some comparison measures that we used, then the actual comparison and a discussion. So this slide really needs no introduction. However, I would like to point out that this talk is in the context of mixture modeling. So a finite mixture model assumes that an observation X comes from a population with G subgroups and has this density F, so which is a convex combination of component densities Fg. So it's not written here, but these pi g's are positive and all add to 1. So probably the most famous mixture model is the Gaussian mixture model. It holds a very special place in the literature. It's firmly established. It's been used for high-dimensional data, co-clustering. Pretty much anything that you can think of, it always starts off with a Gaussian assumption, mainly because of the mathematical tractability. However, the Gaussian mixture model does have its pitfalls. Mainly, it oftentimes overfits the true number of clusters when there are either skewness or outliers present in the data. So to combat this, many different methods have been proposed to deal with skewness in a cluster analysis, and they mainly fall into two categories. The first is the use of skewed distributions. So this basically just fits a finite mixture model with each component being modeled with a skewed distribution. So for this comparison that we did, we're specifically looking at skewed distributions that arise from this variance mean mixture model, and it assumes that X can be written in the form in that second line there. So mu is a location parameter, W is a positive random variable, alpha is a skewness, and V is a multivariate normal random variable. So many distributions arise from this form, namely the variance gamma and the generalized hyperbolic, which we use as our representatives. But we also have the skew T and the normal inverse Gaussian. So the variance gamma arises when W is taken to be gamma with parameters gamma and gamma. So gamma is greater than 0 and is a concentration parameter. The generalized hyperbolic distribution comes about when W is a generalized inverse Gaussian as parameterized by Brown and McNicholas in 2015. And omega is a concentration parameter and lambda is the index. So just a few properties. These are their densities of these distributions. I won't get into the nitty-gritty, but I would like to draw your attention to the terms in red and blue. So delta here is the squared Mahalanobis distance, and rho is this positive quantity. So one of the pitfalls of the variance gamma is the infinite likelihood problem. So this occurs when delta goes to 0 due to an observation becoming very close to the location parameter. And then if this is the case and gamma is less than p over 2, then this red term goes to infinity. So this isn't too surprising since the variance gamma is basically the shifted asymmetrical plus distribution plus concentration. And the Sal distribution is well known for having this infinite likelihood problem, so it's not really that surprising that the variance gamma also has this problem. However, for the generalized hyperbolic distribution, and actually the skew T and the normal inverse Gaussian, this is not the case because this omega parameter there basically saves this when the delta goes to 0 and lambda is less than p over 2. So for the purposes of this talk, although not great when p is large, if the estimate of the gamma parameter is less than p over 2, then we just set gamma to be equal to p over 2. So the second category of dealing with skewness is in the form of using transformations and clustering simultaneously. It was presented by Zhu and Melnikov in 2018. So basically, if X is your p-dimensional vector of interest, then we assume that there exists this transformation vector lambda such that yg, which is equal to the vector with each of the x's transformed, is approximately normally distributed. So we considered two different transformations, namely the power transformation from Yeo and Johnson in 2000 and the Manley transformation from 1976. If you want to take a look at all the math and nitty-gritty, go to Zhu and Melnikov 2018. Okay. So for means of comparison, we wanted to look at cluster skewness and cluster kurtosis. So we considered Mardia's skewness, although old, can be effective. So we look at his measure of multivariate skewness and kurtosis. We could look at each of the dimensions separately for their skewness and kurtosis, but then for higher dimensions that could get messy. So under multivariate normality, the skewness is equal to the skewness is equal to 0, and the kurtosis is equal to p times p plus 2. So therefore, when reporting measures of kurtosis, we will report the estimate minus p times p plus 2, so that negative kurtosis corresponds to lighter tails, positive corresponds to heavier tails. And you can also test to see if they are significantly different than what would be expected under normality. We also consider cluster overlap, which is similar to that used in Melnikov 2016. And so the basic idea is to estimate the probability density for each group, and they have relative proportions pi 1 to pi g. Then for each group in turn, you simulate endpoints from that estimated density, and then you classify each of the endpoints to the group that maximizes the prior probability times the estimated density at that point. And so therefore, you can then look at how many points are misclassified, as well as the points that are correctly classified, and then you can look at a matrix, which I'll show in a second. So as far as estimating the density, we wanted it to be easy to simulate from, of course, but also capture skewness in the cluster. So we looked at two possibilities. First, fitting a finite mixture model of Gaussians to each component separately, but also we looked at kernel density estimation. So I won't get into the details, but we used a Gaussian kernel with Silverman's rule of thumb. So because I'm trying to cut back, I'll just go straight to these overlap maps. So this is for the iris data set, which of course everyone knows has two groups. The first group is well separated from the other two, and then the other two have some overlap between them. So using the Gaussian mixture, we see that 100% of points coming from group 1 are correctly classified into group 1, 98 for group 2 with 2 misclassified into group 3, and with group 3, 97 correctly classified, 3% misclassified to group 2. With the kernel density estimate, we have more overlap between groups 2 and 3. The reason for that is that when using kernel density estimation, there is equally likely to choose a point on the outlying part of the cluster as the internal point of the cluster. So depending on your philosophical bend, the Gaussian mixture can be considered liberal and the kernel density estimate to be conservative. So to get as close, well, to make sure that the results are not truly affected by initialization, what we did is that we looked at tons of initial points and then ran from each of these random starting points, we just ran it to convergence. So we looked at k-means, we looked at 1,000 random soft starts, 100 times g random hard starts using one iteration of the k-means. And then also we looked at hierarchical initialization using Ward's linkage. Okay, so for this, we looked at a bunch of real data sets because to simulate with all these different things to consider, the number of possibilities can get very large. So we looked at tons of different data sets, and I'll just report the findings for a few of them. So first of all, with the iris, all four different methods choose two groups instead of the correct 3. The ARI is exactly the same for all of them. We see from the Skewness and Kurtosis that each component is approximately normal, and then we show these overlap maps like before. So the second data set is the 13 variable wine data set. So this is still somewhat a work in progress, and we are just fitting unconstrained covariance to each component. We will be looking at using constraints in the future and parsimonious models. So we see that all four, once again, fit 2 groups instead of 3, but that could either be due to the kurtosis being significantly negative in 2 of the 3 clusters, but it could also most likely be to the dimensionality. Okay, And we see from the maps that the groups are fairly well separated. So the diabetes data set looked at 3 different types of diabetes. So in this case, all 4, once again, very similar in performance, finds 2 groups. And so 145 observations in total for 3 different types of diabetes. From the map, we see that there's bit of an overlap between groups 1 and 2. What's my time like? 4 minutes? Oh, okay. So I'll skip over that. So then the bankruptcy data set, it has 2 groups, financially sound firms and bankrupt firms. And so in each case, the skewed models and the transformations, they all fit one group to this data set. And we see that the overlap between group 1 and 2, from the KDE at least, is somewhat substantial. And we also see that the first component is significantly non-Gaussian, where the first component is, the second component is Gaussian. And if we look at the plot of the data, we can see why skewed models might fit one group to this cluster. We see that there is a very symmetric cluster overlapped with a skewed cluster here. So in a true cluster analysis, would that actually be one group or 2? And so the skewed distributions or transformations, due to their flexibility, might not always be the solution, because we might end up actually missing one possible underlying group that is quite important. At this point, don't know of any possible solutions to deal with that. So the AIS data set looked at males and females. We looked just at the trivariate data set, looking at BMI, body fat, and lean body mass. So once again, very similar performances between the skewed models and transformations. However, the variance gamma does have quite a few more misclassifications. They all choose the correct number of groups, so using the BIC. However, one interesting thing to note is that the generalized hyperbolic actually has 3 misclassifications for females, 1 for males, whereas the transformation methods have 2 of each. Now, I'll end with this one interesting situation for the Krabs data set. So here, as everyone probably knows, the Krabs data set has 4 underlying groups, or 2, depending on, think about that. So there are male blue crabs is the first group, female blue crabs is the second, male orange crabs the third, and female orange crabs the fourth. So we see that the skewed models detect based on the species, and the transformation methods detect the sex. From the skewness and kurtosis for each of these components separately, there's really no indication as to why this might be the case. However, one interesting thing to note is that with looking at males and females separately, the males seem to exhibit insignificant skewness. However, for the blue and orange crabs, so the species, both exhibit skewness. And in all cases, the kurtosis values indicate that there's no significant non-zero kurtosis. So one possibility that we'll potentially look at using simulations is that whether or not, if presented with a symmetric group, will the transformation methods be more likely to possibly detect that group? So maybe simulate something similar to the Krabs data set. Okay, so I'll finish now. So in summary, skewed distributions or transformations, as we sort of expected when we went in, there is no clear best method. However, there were completely different results for the Krabs data set, which was somewhat interesting. And then using one or the other might actually just come down to interpretability. The skewed distributions allow for a direct modeling of skewness, and therefore you get an estimate of skewness. The transformation methods, little less easy to interpret. However, this transformation methods do have fewer parameters. So the next steps, like I said, extensive simulation studies, more investigation of that cluster overlap measure, since we got some weird results in some cases. And then also, are there similar results in the matrix varia case? So I would like to thank my collaborators, my supervisor, Dr. Paul McNicholas, Dr. Vladimir Melnikov, and Dr. Zhuan Zhu. And this work was supported by the Canada Vanier Graduate Scholarship, the Canada Research Shares Program, and an NSERC Discovery Grant. Thank you.
Any questions?
Michael, I think it would be of interest to also include the C-bus.
Yes. Yeah, we were talking. Yeah.
There's an arbitrary directions in
Yes.
the feature space rather than in directions parallel to the axes like the transformation.
Yes.
But also, there's a very nice paper by Bickle and co-author about transformations, and perhaps a bit critical of it, but then Box and Koch write a rebuttal, and
Yeah.
they really say that perhaps you should decide on the scale first before you apply the transformation, because they presented an example where you could transform the data, still be normal. You could take some normal data, still transform it to normal, but then you wouldn't get a significant difference between the groups. So there's, it's a very sort of complicated problem.
Both methods that you presented identified just a single group on the credit.
On the bankruptcy, yes. Yeah.
Usually bankruptcy data is heavily unbalanced with regard to the number of occurrences. So unbalanced in the original paper, there were only a few bankrupt companies.
Yeah.
Did you work on a balanced version of the data set, or
Yeah, so the bankruptcy,
just on the original, the raw data?
so yeah. Yeah, 66, 33 from each group. So you're asking if we worked on,
Yeah, but you provided some I would say some, whether you increased or whether you used a kind of balanced sample or not, from this bankruptcy data set.
so this bankruptcy data set that we used was available in R. I should have probably mentioned that.
It's a huge difference how you treat the imbalance of the chances.
Yeah, yeah.
And if you really properly
yeah, we will, yeah, yeah, we will look at that. Thank you. Yeah, yeah, for sure. Yeah.
Probably we have time for one more question if there is any. Right, let's thank Mike once again. Our next speaker is very patient.
Thanks. Yeah, I think this one. How much time do I have? Just cut me off if I'm going along. All right. What's that? Okay, thanks. It's good to be here. I'd like to thank Vladimir for organizing this session and allowing me to be part of it. I'm going to be talking today on some work that Jose Quinlan, who was a PhD student of mine when I was down in Chile, he did a lot of the heavy lifting. And, but we're going to be talking on a project that was part of his particular dissertation on a class of repulsive mixture models. And so I'll just get started. So I'm going to be using this well-known data set. Galaxy data is well known to anybody that does any type of density estimation using finite mixtures or mixtures generally, right? And so we'll be using this. It's very common to use a finite mixture, and the finite mixture was introduced quite well in the previous talk. But the key here is from at least from a Bayesian perspective, it's very common to model the component means using an IID type process, right, or an IID type model. And so that's what we're interested in kind of exploring is kind of relaxing that assumption so that we can produce mixture models that are more parsimonious. And I'm going to kind of try to define that in a very clear way as we're going along. So here, just to be completely complete, these are our observations. They could be d-dimensional. These are our component means. We're going to be talking about Gaussian mixtures. These are component covariance functions, and then we have the weights associated with each one of the components. And sometimes K is either going to be finite, that's a finite mixture, or it can also be infinity, which is then an infinite mixture. And both of them have been considered for and developed, and a lot of work has been dedicated to those types of models. It's very common also to facilitate fitting these models to introduce a latent cluster label, if you will. And once we know where the cluster label, and once we have the cluster label, then we've identified to which group the individual belongs, and then so we're able to formulate a hierarchical model here, where given the cluster label, we know he's in the d component, or she, and then we put what is that called? A multinomial, if you will, Dirichlet hierarchical structure on the latent cluster labels, right? And so what we did is, just as a preliminary approach, we fit an infinite mixture model using the DP package here in R to these data, where, once again, I want to highlight the fact that these things here in that particular model are modeled IID. And so this was the result. A very nice density fit, right? I mean, it's very flexible, and it seems like it follows the data quite well. The thing that I want to put emphasis on is perhaps the component means, right? So in that particular setting, the number of components is infinity. And so once we've estimated the partition, then we are able to get the means associated with each one of the clusters in the partition. And it seems like there's a bit of redundancy here. There's two here, maybe one cluster would have been, or one component would have been sufficient there. There seems to be two here and two there. It seems maybe one is sufficient there as well. And so our idea then is what can we do to kind of relax that IID assumption, because that's the thing that's driving that, right? There's no structure in the model impeding cluster means to be close to each other. And that's what we kind of want to relax that. We introduce kind of a modeling technique that introduces a bit of repulsion, where we kind of push the cluster means apart, right? With the idea of being more parsimonious. And that's kind of what motivated this particular work. Okay, is that making sense? Kind of at least the idea, what we're trying to get at? Okay.
All right. So the flexibility, at least from a DPM, Dirichlet process mixture model, comes at a cost. Oftentimes there's a lot of unnecessary clusters, and to create that flexible fit. We found that the average number of clusters actually turned out to be 10 with this. Admittedly, this might be a behavior of the DPM rather than if we used a finite mixture tends to, in its partition model, it tends to flatten that out a little bit, where a DPM kind of favors a lot of small clusters. Okay. And so we wanted to do something there that was parsimonious, a parsimonious mixture model, without sacrificing too much flexibility or model fit, right? In other words, we want to make sure that these cluster means are well separated, right? Okay. All right, so that's kind of the motivation, what we're thinking about doing. In our approach, before I get into our approach, just to make kind of clear here, we're going to be talking about finite mixtures with a fixed number of components. But that doesn't mean that we're necessarily estimating, we're fixing the number of clusters, right? I want to make clear that there's a difference between the number of components k, right, and a smaller k here, which is the number of clusters, right? So k is essentially a capital K is the upper bound on the number of clusters, and the data kind of informs how many clusters there really are. So we're going to be inducing a prior on the number of clusters, even though we fix k at some high value. And there's been a few papers that come out in the literature that's kind of emphasize this just recently. There's been a Miller paper that came out in JASA that talked about this in finite mixtures. And there's one that Argento and Diorio is working on now that also, from a point process perspective, also talked about this, right? So our approach to introducing repulsion is through these things that are called Gibbs measures, right? And in particular, Gibbs point processes. These are used regularly in mechanical statistics. They model the average microscopic and microscopic states of the system. And so we're able to kind of inform exactly how we want those points within the system to behave. In other words, if we want to introduce a little bit of repulsion, we can do that using this particular approach. So we want to construct a Gibbs point process with that idea of repulsive in there, and then through this construction, derive a probability distribution that has the repulsion characteristic parameterized directly into the distribution. That was kind of the idea. Okay. So by definition, this is kind of going to be the construct that we're working with. We have two functions in here. This one right here is kind of an environment influence that this has on the process, and this right here is where all the action's going on. This is where we can potentially put in repulsion, because this has to do with interactions. At the end of the day, repulsion is essentially an interaction between 2 points in a point pattern, for example, or a point process. This is the product, Cartesian product of these Borel sets, and we have, these are measurable functions, and so our goal then is to choose a gamma 1, or a phi 1, sorry, a phi 1 and a phi 2, I think that's phi. That's phi, right? I think so. Phi 1 and phi 2 such that this thing right here is finite, right? And if it is finite, then that means we can create a probability distribution. That, at the end of the day, that's what we're most interested in. Okay? So, like I said, this is where all the magic goes on. If it's not equal to 0, then it's common to define some sort of distance metric. That's what this row of x and y is going to be, a distance metric between x and y, and then this phi function is essentially going to determine how much we're going to penalize for distances, essentially, right? And so the interaction comes into play with this distance matrix, right? This distance function here. Okay? And so these particular choices are what is going to allow us to induce this repulsion, and then also the strength of the repulsion between points, right? And once again, we're interested in using this repulsive idea in modeling the component means of a Gaussian mixture model, right? Okay. We're not the first ones to actually think about this. There's some folks that use point processes to incorporate repulsion directly, and there's actually a paper, Petrelli et al., who did it in terms of modeling, and then there's also another approach, non-local priors. This is actually just coming out in JRSSB just now. And then there's one other approach that I didn't put this in, that just came out in JASA recently, about introducing repulsion. What distinguishes us a little bit from those other works is the type of repulsion that we're able to introduce and the generality that we have of being able to introduce repulsion that is very strong or very soft. And we're able to kind of control that a little bit. We don't want to push points too far apart, right? We want the right amount of repulsion. Okay. All right. So within this, so I'm going to define, first of all, with this probability distribution, the repulsive component. So we take some C function that has these particular characteristics. As it goes to 0, then it's 1, right? And as it gets really, really large, then it goes to 0. There's no repulsion, essentially, and there's really strong repulsion in these two cases. And then we're going to define the repulsive component of the probability distribution with this RC. It's just going to be this particular product here, right? And so we're going to try to connect this with what I had written here, right? So I got to define this, and I got to define this suitably in terms of this particular component, so that we're able to derive the probability distribution that has that characteristic of repulsion in it. So this is the repulsive part, right? Then we also have, like, if you would, like a base distribution, this F naught, and we're going to usually assume that this is Gaussian. And so this is essentially what our distribution looks like, where our phi1 is equal to that, and phi2 is equal to that, and then this thing that I defined last a couple slides ago can be derived as this right here, right? And it just turns out that this right here has a finite integral, and so then we can divide by the normalizing constant, and then we have a distribution where repulsion here is parameterized completely into it. If there is no repulsion, then we just kind of fall back onto the IID modeling that we had before, right? Okay. So this right here, this part of the probability distribution is what's introducing the repulsive part. Without it, we just have the IID model that is typically used. All right. And so here is our probability distribution. We're going to denote this as a rep distribution with number of K is the number of components, D is the dimension. And once again, repulsive part, IID part. If this goes to 1, then all we have is our regular IID model, right? Okay. Yeah, not to spend too much time on this, a couple properties is it's not sample size consistent, which is kind of an unfortunate thing. That means if you have a sample size of n+1 and you want to find the distribution of n components, you just can't integrate out that n+1st component because it depends completely on what happened before, where you can actually put those things, right? If you think about it, if you think about a conditional construction of this, if you have a point here and there's repulsion, then you're reducing the amount of probability that could be close to that, so the other point has to be over here, right? And as you fill in that space, then you just don't have very many points that you can put them as it gets bigger, right? But we do have an exchangeable distribution of the x's through x1, and that's through the symmetry coordinates of the particular repulsion distribution. Okay. All right, I'm going pretty fast here. So the only thing that's changed, so we're going right back to our finite mixture model that's kind of written in hierarchical form. The only thing that we've changed is instead of modeling this with an IID Gaussian, we're now modeling this with this Gaussian repulsion. And I'm going to give you the exact details associated with this distribution in the next slide. But I want to highlight the fact that this model, the formulation of this model, particularly this part, that part, and this part, right, these three levels of the hierarchical model, induce a prior distribution on the number of clusters. We can't write that distribution down, and it is influenced by this repulsive component as well, right? And so even though it's a complicated thing that we can't write down, there is a prior that's implicitly induced on the number of clusters, even though we fixed the number of components to some upper level, if you will, upper bound. Okay. So these are these here are the exact details of the components we used in the particular repulsive distribution. We're going to set the base measure just a Gaussian, the base distribution. So that means if there is no repulsion, then we just kind of fall back to an IID Gaussian model for the components. This is going to be our function here, where repulsion is parameterized by tau. So as tau controls the strength of the repulsion. As tau approaches 0, the repulsion becomes weaker. As tau gets big, that means we have a lot of repulsion. And then we're kind of measuring the distance using Mahalanov's distance between these coordinates, right? And that's going to be influencing the amount of weight we put towards the repulsion or not, right? And so this NREP will favor concentration data around well-separated locations, theta j, and that's kind of what we're looking for here. Okay. I'm not going to go into any details, but we studied the theoretical properties of this model. We've developed some MCMC techniques to fit the model. We suggest standardizing the responses because then that facilitates selecting values for the prior. At this point, we would like to have tau, the parameter that influences the amount of repulsion, we'd like to have that be an unknown as well. But assigning it a prior is problematic because it makes the process doubly intractable. And that's just a hard thing to deal with, and so we fix it. But we've come up with ways of estimating it intelligently and using it in the modeling process, right? And so we fit this model here to the galaxy data and another bivariate data set called air quality data. These are both readily available in R. And we compared it with this Dirichlet process mixture model fit. Notice that the fits are very similar in terms of the density estimation in both the univariate and the bivariate fits. And that's what we were hoping for. We didn't want to sacrifice too much model fit for the sake of parsimony. 4 minutes, all right. LPML is a metric used to assess model fit. Higher the better. We actually do fit the data better in the galaxy. We slightly fit it worse in the air quality, but notice that the mean number of clusters is quite a bit smaller here. Here it's just slightly smaller because there's really two well-defined clusters in this particular data set. And the standard deviation associated with the posterior distribution of the number of clusters is quite a bit smaller in the model that we derived or we developed. And here, this illustrates that even more. This is the posterior distribution, the number of components. Red here is the repulsion, and so we're forcing these points to be far apart, which is concentrating the number of clusters closer to 5 or 6, whereas there's a lot more spread when we're using the Dirichlet process mixture. And then here is the case for the quality air data. And once again, I mean, this could be an artifact of what's going on with the Dirichlet process mixture model. And so we decided we wanted to compare it to a finite mixture, so we did a simulation study, which I don't have a whole lot of time to detail, where essentially what we did is we generated bivariate data, right? That has 4 components. These components have overlap, and we wanted to see how we do when we generate a bunch of data from this particular data generating mechanism. We compared ID Gaussian with repulsion using 3 different types of strength of repulsion. This hardcore potential is a lot of repulsion. The one that we suggest is based on this Ogata and Tanamura type potential, which is softer, and this is in the literature, which is a little bit harder. And just to get an idea of the differences in the type of repulsion, we generated a bunch of data, a bunch of observations from the bivariate NREP distribution. And this right here is tau. Notice as tau grows, that means the repulsion increases, and then we're looking at the distance between the two coordinates that we generated in the bivariate NREP distribution. So obviously when there's IID, the distance is not impacted. This is the hardcore, and so you can tell that there's a lot of repulsion here as tau increases, whereas this is quite a bit softer. Ours here is the dashed one, and this is the dotted one with the Petrali et al. So ours is probably the softest amount of repulsion among those 3 that we considered. Are we doing 2 minutes? Okay. We wanted to study if we increase the maximum number of components, the strength of repulsion, and the sample size. LPML, the story here is notice that all the fits are essentially the same unless we introduce too much repulsion. So the notion of too much repulsion is possible here, and it negatively impacts the fits. Other than that, the fits are essentially identical to using a finite mixture model, and that's what we had hoped for. The number of active components, as we introduce more and more repulsion, notice that the number of clusters, or what we're calling active components, reduces from what this finite mixture is, which is the red, and that's kind of what we're hoping that the repulsion would do. In fact, the purple, once again, is hardcore repulsion, so it's too much repulsion. And then you can also see with the minimum relative distances between components that the finite mixture model has the smallest one, and as we in which we expected because there's no control over, or there's no structure forcing points to be far apart. All right. Wow, that was kind of probably faster than it should have been, but we're at the end. So we developed this model-based procedure that introduces this idea of repulsion directly in the modeling. It can aid in partition interpretation also because it will reduce the number of singletons, which is something that's common with these Dirichlet process mixtures, not so much so with finite mixtures. And also in stuff that I did not present today, we also considered repulsive density regression methods, where we introduce a covariate. But we followed the same approach. We just augmented our data vector with a covariate vector and followed the exact same modeling procedure. And I guess that's it. Those are the references.
Any questions?
Yes, so this was very interesting. Now, at some point you emphasized the difference between mixture components and clusters.
Yeah.
I'm not 100% sure whether what you meant by this would be the same as what I mean by this. If I think about this difference, I would say, well, of course, a mixture component in itself doesn't imply that it is well separated from other mixture components, right? So you can have one thing that you would want to interpret as a cluster and three mixture components fitting it, right? Like you showed in the galaxy example, and then you would say, well, that's maybe three mixture components, but only one cluster. Now, if you are now starting to claim that what you're doing here rather gives you the clusters than the mixture components, I gotta say I'm a bit confused because if you basically emphasize that mixture components are normal but the clusters are not, why does it make sense to go on with a method where the clusters still are normally distributed, right? And the result of what you're doing here kind of shows that you are somewhere halfway between them, because if you look at the galaxy data set, I think anybody would be hard pressed to see more than 4 clusters there, but you are kind of saying, okay, I don't want to sacrifice so much fit, so I'm kind of happy that I have 5.37 or something. However, what qualifies these 5.37 as to be interpreted as clusters if the 8 that you previously had are not qualified? I don't see if in an example like this you end up with a number that is substantially higher than 4, how you can say these now should be interpreted as clusters.
That was a good question. And truth be told, just standing here, I don't know the best way to answer that. I'll have to think about it a little bit, but you're exactly right. I think interpreting, maybe I'm just going to start rambling and probably not answer exactly what the question was, but I find the more I work in this clustering and trying to interpret what a partition and the clusters within a partition is, it's not straightforward in the least. Particularly in when we're trying to identify what is really a cluster and what really isn't a cluster, right? When we don't, I mean, this is, if we don't know the truth, right?
What about starting with the definition? So saying, I mean by cluster the following thing, and then you can put up a method, and then you can
absolutely
show that the method finds the
yeah.
ones that you have defined to be the true clusters.
Yeah. That actually is a good approach, and maybe one that we should take here actually. Yeah.
I mean, I should actually say that later today I will talk on the number of clusters, and I will not do this thing either.
Okay. Well, I look forward to your talk then. I look forward to the talk. But that's actually not a bad approach to define exactly what your definition of cluster is at the beginning, and then move forward with it. Yeah.
Unfortunately, we're running out of time, so if we have any other questions, we should ask Gerrit after the session. Okay, let's thank Gerrit again. Our next speaker is Mike Porter.
Okay, thank you. We will get into it. So we're also going to talk about the issue of finding partitions that may indicate groups or clusters. This is work that I did with one of my graduate students, Kitong, who's now at Amazon. And so we're going to try to address this question somewhat of what's the goal of clustering. And one of the goals is to discover partitions that assign observations into meaningful groups. Now, there's different ways, as the last question just brought out, to define what's a meaningful group. Is a meaningful group one where the observations come from the same distribution? Or is a meaningful group, another way to look at this kind of from the computer science side, is sets of observations that are more similar or closer to observations within the group than those in other groups. And we're going to kind of look at it more on the partition side related to components of distributions. And so one application of this is when you have a model-based clustering from a Bayesian model, for example, in this process of fitting it in the MCMC samples, you get a set of partitions. And we want to try to take this set of partitions and combine this information together to extract one kind of optimal partition. So we're kind of in a Bayesian world some way, but then we want to kind of get out of that and just come up with one point estimate of the best partition. And so our approach to do this, well, let's give an example. So at the top left corner, you'll see a four-component model, events generated from four components, four distributions. And then you see the other facets are related to the partition derived from some sampling from the MCMC step. And so some of these samples have four components. Some of them have five components. Some of them have six components. We could get different components in here. And you can also see that there's the issues related to observations. Some of them are defined to the right group. Some are defined to the wrong group. We have overlap, of course. And you also have this issue of label swapping. So what's group one in the top left, it's clear that that's a different group number in some of the other samples. So we want to be able to combine this information from a set of partitions and come up with one. So we have n observations, and we also have n then partitions. So a partition vector is just the set of membership that each observation gets assigned to. And we're going to have in total big M partitions based on MCMC sampling. And again, the number of clusters for each one of those could be different. One way to combine this information is with the posterior pairwise similarity matrix, pi. So pi ij, by definition, is the probability that the cluster label for observation I is the same as the cluster label for observation j, given the data. We can estimate this very naturally with just the sample proportion. So for every ij pair, it's just the proportion of times that those two were assigned to the same component across all our big M samples. Now we're also going to use a loss function approach, and what would be then by definition the optimal partition is the C star that optimizes our posterior expected loss. And we can also then have a natural estimation for our posterior partition is just based on, again, the MCMC steps. And so really the goal here, the way that we're looking at it in simple terms, is just find this C star that maximizes the posterior loss, given the data that we have. Now to take this a little more general, I'm going to step away slightly from this notation of posterior expected loss, because we may need to make some approximations to that. Some of the current methods in the literature do this, just that. So to make this as general as possible, our goal is to find C hat, the partition, that minimizes some penalty function that ideally would be based on some expected loss, but in reality may be something slightly different than that. We're going to have a search space. So this could be exhaustive, so we could try to look at all possible partitions that we could have for n observations, which would be pretty extreme. And then we also need some sort of optimization algorithm to find the optimal partition within this search space that we're looking at. So I'm going to talk about three different loss functions that have appeared in the literature that we're aware of. The first one is called Binder's loss. This was the original approach that came out, I think, in the 70s or maybe early 80s. And basically it's a natural loss function. So we have pi hat, which is what we get from our MCMC samples. This is just the pairwise probability, empirical. And then we also have the indicator function that in our candidate partition, that the label for I is the same as the label for J. And we're just going to look at the absolute value of the sum over the n choose 2 pairs that we have. This also is equivalent to the RANDS index, so this is a common approach to measure the correspondence of clusterings between two partitions. So Binder's, when you think about this, you could think about the RAND index. Another kind of name for this is Dahl's paper. He introduced a loss that's the squared difference between the sample proportions and your candidate predictors. And it turns out that this gives equivalent optimal partitions. So you can kind of work this out as the Binder's loss plus some constant that's not a function of your candidate partition. And so you can kind of recognize those depending on how you're used to thinking about comparing partitions. The second one is called the Pair Criterion. This is based on now the adjusted RAND index. And in the paper that introduced this pair metric, and this is the reason that I kind of got away from the expected posterior loss, is for computational reasons, instead of attempting to find the expected posterior loss, so the expected adjusted RAND, they actually move the expectation inside this summation. And so now they're going to look at the adjusted RAND of the expected partition vector. And so what this is going to do is, it's going to simplify computation. It's going to make now our penalty function just show up with these pi hats. So it's basically going to take the penalty function and make it be modeled from this posterior pairwise probability. So computation becomes very fast and very easy for this. And so this is, but it's an approximation of the adjusted RAND. And of course in the paper, this pair paper, they show that this is, gives very equivalent results to using the more computational intensive expected posterior loss. And then the third one is based on another measure of cluster comparisons, which is the variation of information. And the same sort of steps were taken. So instead of trying to make this penalty function based on the posterior expected loss, they actually move the expectation inside the loss function. And so again, you'll see now it's this empirical pairwise probabilities is what gets into the function. So it's a little faster to compute. Okay, so these are three loss functions that we can use to try to find a partition that optimizes those. And again, just remember we have to find some way to search through all this, all the possible partitions in the search space. And the way that this is done, because an exhaustive search is infeasible, of course, is two main approaches. One, we can reduce the search space. So instead of looking at all possible partitions, we could just look through the partitions that are based on the MCMC samples. So we have this set of partitions. We can just find the best one out of the MCMC partitions. A second popular approach is to then take this pairwise probability matrix and perform hierarchical clustering on this using whatever linkage you want to use, and then also search through those candidate partitions for the best. Some other approaches are to actually consider the full sample space or space of partitions, but then use some sort of greedy or binary programming as a way to try to find this partition without reducing the search space. Now the approach that we saw is basically recognizing that a lot of these methods were based on this estimated pairwise posterior matrix, is to look at another way to estimate this, which is something called non-negative matrix factorization. And it turns out that this is another way to see this is we're also coming up with new ways to search through the partition space that does a little, it increases our diversity in here. So we're not limited to the MCMC samples, we're not limited to what you get for the hierarchical clustering, and it still performs fast. You can still do this without some of the integer programming, for example. And so this is the approach we take, and kind of putting it into perspective, what these traditional approaches are trying to do is estimate a non-binary probability matrix with a binary partition. And NMF is going to let us actually reduce this restriction of binary to allow non-binary, but we can still extract cluster information from this, so kind of make hard classifications from it. The setup for NMF, or non-negative matrix factorization, is this equation 1. So we're trying to estimate a matrix as a combination of two non-negative, so the elements in W and F have to be non-negative. So two non-negative components. And the Frobenius norm, so we're just looking at the squared, the sum of the squared difference between our pi hats and W and H. And these are very well-developed methods in NMF to do this estimation. This is kind of the basic iterative approach where you estimate H and W iteratively. There's all sorts of ways to exploit sparseness in this and parallelize it, and there's a lot of routines to be able to do this quite fast, even for large partitions, large matrices. And to try to compare with, it's probably closest related to Binder's method, and you look at the difference between them. On the left side we have this kind of traditional approach with Binder's loss. You see what we're trying to optimize is the sum of the square differences between what would be a pairwise probability and then what we're going to extract from our optimal partition. And then the NMF, it's the same thing, but now instead of over our candidate partition C that are going to be binary, now we have this non-binary W and H that we're trying to estimate. And then to approximate this pairwise components, we're going to use real valued based on WH instead of something that's binary. And that allows us to get a hard partition or a soft partition. So soft partition meaning that we can say that this observation is assigned with some probability to each one of our clusters. And these are represented by the W and H matrices. So the columns of the W matrix are centroids in some sort of space that's undefined here. And H is going to be then the weights, the cluster weights. So we can say an observation is kind of a mixture of these components that's represented in the W matrix. And that allows us to make these so-called hard clusters or hard partitions. So the cluster label for observation I is just the row that maximizes the appropriate column of H. We can also look at soft labels, or kind of a probabilistic sense. So we can get an estimate vector CI soft is now going to, instead of a 0, 1, it's going to be a probability, some real value between 0 and 1, where across I, it's going to, across all the different components that you have in here, it's going to sum to 1. Now, one issue about NMF is you have to pick K. You have to pick the number of clusters that you are going to assume to be in the model. And the way that we do this is just search over the different values of K. So we have NMF. You set K, and that's going to determine the columns of the size of the W and H matrix, and then you just search over K. So we start with K equal 1, and we just increment this up from 1 to whatever we think a possible max may be. Some of the same issues do occur with NMF, so there's some initialization effects. So we'd also, along with selecting K, we're going to do some initialized starts, and there's lots of routines to try to start you in the right place. But again, we're going to do multiple initializations and then run till convergence. There's the equation that I showed you for NMF is kind of the squared error version of it, but there's all sorts of variations. So you could look at something that is more based on likelihood ratios with different non-Gaussian distributions. You can include a smoothing matrix S in between W and H to increase the sparseness in this. You can use an offset component, so you can have some common features across all the clusters included in your NMF. And so here's an example to kind of illustrate how we do the clustering. So this is a 4-component mixture, so we realize these observations from 4 distinct distributions. And the observation numbers is the numbers that are shown. So 31, 32, and 33 are up in the top, and 34 through 36 are in the bottom. And if you run these conventional or traditional methods based on binders and the pair method and the variation of information, you get that there's actually 2 clusters. All of these estimate 2 components with it. And you can see the top one's assigned to the cluster on the right, and these numbers at the bottom to the cluster on the left. So when we run NMF for this, we're going to take, again, a collection. So we fit some Bayesian mixture model. Don't really report the details of that. But what we get out is now some estimate of the posterior similarity. These are from the MCMC samples, and then we're going to use either a kind of this conventional or hard partition, or we can look at the NMF approach, which is going to give us some more uncertainty. It's going to represent that uncertainty better in the matrix. The top is now the loss function. So we see that based on NMF, this is searching over our values of k, that our expected loss is reduced at k equal to 2. So this is suggesting that the best that NMF can find is also 2-component mixtures. But you can see that it's a not very much difference between 2 components and 4 components. These bottom 2 show now the proportions. So that for each one of our, along the x-axis is our observation number. So we see these 2 small clusters, 31 through 34 and 35 through 37 or 36. And you can see that NMF starts to bring out some of the uncertainty in these assignments to the components. So we have some measurement of how uncertain our final partition is. For the for the 4-component cluster, you can also see this uncertainty as well. We also looked at the Krabs data set, and the one that was discussed in the first talk. And we can also look at how these different approaches estimate the number of components as well as the assignment into groups. And the NMF approach, out of the 4 NMF approaches that we considered, the one that has the offset component, so it allowed some of these components to share, some of the different components to share information or have a common distance to a centroid is essentially what this is doing. You can see that they have the best performance as far as both all RAND, adjusted RAND, and the VI metric. We also did. We also analyzed the Galaxy data as well, and looked at the number of components that we could find there, and it varied between, I think, 3 and 5, kind of with the same concept of we're explicitly trying to understand the components as far as the observations that come from the same distribution. I think our next step is actually somewhat in line with the question that was brought up after the last talk, is once we have a result of an optimal partition from a method such as this, can we then go fit another distribution to each one of the components, which may be now a mixture of each cluster may be a mixture model as well, or other ways to do that. So in conclusion, we looked at NMF as a way to kind of expand our search space and also develop some kind of an optimal partition by looking at this expanded search space. And it also gives us the ability to look at the uncertainty in some level of the final partition. And that's what I have. Thank you.
Okay, so we are 10 minutes late, so folks, if we have any questions, please ask Mike after the session. I guess we have a coffee break. There we go. Yeah. Thank you.
Ciao. Senti, io hanno finito la lavagna. C'era però una persona che doveva collegare il Mac. Io adesso non mi ricordo. Però dove sta questo? No, perché potremmo. Se me lo fai venire in attimo qua così lo proviamo a collegarlo, ok? No. Ok. Col Mac loro, sempre che abbiano gli adattatori, perché ci vogliono adattatori a HDMI.
Adattatore bianco, quello bianco.
I Mac sono tutti senza niente, hanno un adattatore particolare e esce una scatoletta che ci può attaccare HDMI. Se ce l'hanno bene, se no la loro presentazione la salvano in PDF e la mettiamo qua. Come hanno fatto questi tre che hanno fatto adesso.